So I want to begin by discussing some of the classical motivation for the problem that we're considering. So in this talk, A will denote an abelian variety over a number field, which will denote by E. And for convenience, I'll assume it comes with some fixed embedding into the complex numbers. So this is a number field. Okay. And in this talk, we're interested in studying the system of ℓ-adic representations associated to the Tate modules of A. Okay, so I'll fix L to be a prime, and then I'll let gamma E denote the absolute Galois group of E. Then it's known that there's an action of this absolute Galois group on the ℓ-adic Tate module, L of A, and I'll base change this to QL, so I have some representation in a vector space. Okay. So this action gives rise to a representation called rho L from, oh, sorry. I already broke it. Sorry. Try and press more softly. Okay. Okay, so this gives rise to a representation from the absolute Galois group into GL2G of QL. So here G is just the dimension of the abelian variety. So a fundamental result about these system of representations is that they satisfy some kind of L independence property. Okay, so we have the following result of V, which says if V dividing P, and for simplicity, I'll assume P is not equal to L, so P is some rational prime, and V is a place of E dividing P. Okay, so this is a place of E where A has good reduction. Then it's known that this representation, you restrict the decomposition group. At this place, it's unramified, and the characteristic polynomial Frobenius acting on this ℓ-adic Tate module, this place B. A priori, this has coefficients in QL, but it's known that this, in fact, this characteristic polynomial has coefficients in Z in the integers, and it's independent of our choice of prime L. Okay, so this is a very well-known result. So this gives some kind of compatibility between these representations at the places of good reduction. But one can ask, is there some kind of compatibility at a more general place? And the answer is yes, but it's a little bit more subtle to state. So for this, I have to introduce Weil-Deligne representations. So now if V is a general place, then again I can consider the restriction of this representation to the decomposition group at this place V, which I'll identify with the absolute Galois group of the completion. So in this case, the representation is no longer unramified, but it's still known that in this case the unipotent, the inertia still acts in some kind of nice way. So it's known that there's an open subgroup of inertia which acts unipotently. Okay, so this is the ℓ-adic monogeometry theorem. And so this allows us to associate to this representation of the decomposition group a Weil-Deligne representation. So I'll call this rho L V WD. So this is a Frobenius semi-simple Weil-Deligne representation over C of the complex numbers. So I'll remind you, Weil-Deligne representation really you can think of as a pair, rho prime, where rho prime is a representation of the V group, and N is some nilpotent 2G by 2G matrix. Okay, and for this, to be kind of precise, I should really fix an isomorphism between QL bar and C. Okay, so the point of introducing this Weil-Deligne representation is now in this definition of Weil-Deligne representations, this really makes no mention of the ℓ-adic topology, so we can kind of directly compare these Weil-Deligne representations as L varies. Okay, then in this case, we have the following kind of compatibility result between these Weil-Deligne representations, which I'll attribute to Deligne and Raynaud. So in fact, I think the following result, the statement appears in a paper of Deligne from maybe the 70s or the 80s, but the first proof I could find was in a paper of Raynaud. which says that these Weil-Deligne representations, okay, the isomorphism class, or equivalently the GL2G conjugacy class of this Weil-Deligne representation is actually defined over Q. So precisely this means if you apply any automorphism of the complex numbers to this Weil-Deligne representation, you get back a conjugate one. So it's defined over Q and independent L. Okay, so independent L, here I'll say explicitly, means that for different primes, L and L prime, these Weil-Deligne representations are conjugate in GL2G. All L not equal to L prime. Okay, and here this is my notation for conjugacy. Okay, so this is notation for conjugate in GL2G. Okay, so we can kind of summarize these two results as saying the system of representations, L runs over the prime numbers, forms what's known as a strongly compatible system. What's this? Strongly compatible system. Okay, so in fact, there's also kind of a result for L equals P, but it's a little bit more subtle to state. So I'll stick for simplicity to the case L not equal to P in what I do. Okay, right, so this was kind of the classical theory. And the problem I'm going to consider today is in some sense a motivic refinement of this result. I'm going to consider the following refinement. And for this, I need to introduce a Mumford-Tate group of the abelian variety. So G will denote the Mumford-Tate group of A. So this Mumford-Tate group, so this is a reductive group over the rational numbers, and it's constructed as a subgroup of GL of the Betti cohomology of the complexified abelian variety with rational coefficients. And it's in fact the subgroup which stabilizes all the Hodge cycles. And so this Mumford-Tate group, in fact, tells you a lot of information about the abelian variety A. So, for example, if the Mumford-Tate group is a torus, this just tells you your abelian variety has complex multiplication. Okay, so the important thing here is that this Mumford-Tate group really only kind of depends on the complex abelian variety. And so a priori, you don't really expect any kind of nice interaction with this more arithmetic structure, the Galois representation. But in fact, there's a really remarkable result of Deligne, which tells us that they actually do interact in a very nice way. Okay, so in fact, Deligne's result on absolute Hodge cycles, so this theorem usually goes by the name of Hodge implies absolute Hodge, tells us that we can replace our number field E by some finite extension. So there exists some E prime over E. Finite such that for every L, this representation, rho L, actually factors through a representation into the Mumford-Tate group. So I'll call this rho LG. So this is going to be a representation of gamma E into G of QL. Yeah. Sorry?
When you said there is a prime such that something
finite such that for all L. Oh, sorry, yeah, E prime. Yes, yeah, thanks. Yeah. Great. So yeah, in general, you have to make this finite extension. And the kind of the heuristic for this result really follows from the Hodge conjecture. So if you believe the Hodge conjecture, one should expect this kind of factoring result, and you can think of Deligne's theorem as some kind of reasonable substitute for the Hodge conjecture in the case of abelian variety. I should move it up. Oh yeah, sure. Okay. That's better. I can't reach that one. Okay. So let's assume, without loss of generality, that we've made this extension. So we have this backbone property. Okay, so then a very kind of natural question arises, which is whether this kind of L independence occurs for these representations valued in the Mumford-Tate group. Okay, so precisely we can ask whether, okay, if you restrict this representation to the decomposition group at some place, in this case, you'll get a G-value Weil-Deligne representation. And you want to ask if for different primes L, these Weil-Deligne representations are conjugate in this smaller group G. Okay, so it's a kind of a stronger notion of conjugacy. And so state this in the following conjecture, we'll call conjecture A, which is that these representations for LG as L prime forms a strongly compatible system of G-valued representations. Okay, so I'm going to say kind of precisely what this notion of strongly compatible means in a moment when I state the main theorem. It's again going to be just what I said about this compatibility of Weil-Deligne representations at each place. So maybe let me make a few remarks about this conjecture. So I guess one can think of this as some kind of folklore conjecture, because I'm not sure it's ever been, at least this precise statement's been written down somewhere. At least I couldn't find it. But you know, there are certain special cases which I think have appeared. So, for example, the compatibility at places of good reduction, I think, appears as a special case of a conjecture of Serre in his article in the motives volume. But in any case, once you kind of have this backbone property, this conjecture is really a very natural thing to consider. Okay. So the main theorem I'm going to discuss today is about kind of verifying this compatibility condition, the definition of strongly compatible system for certain places of the Noah field. Okay, so to state the main theorem, you need to introduce these G-valued Weil-Deligne representations. Okay, so now if I restrict my representation, my G-valued representation for LG to the decomposition group, this gives rise to rho LV WDG. So this is now a G-valued Weil-Deligne representation. So in this case, this is going to be a pair rho prime upper G and N upper G. Okay, where this rho prime is now a G-valued Weil representation, and N, as opposed to being some nilpotent matrix, is going to be a nilpotent element of the Lie algebra. Okay, so NG can be nilpotent element of the Lie algebra. Okay, so this is a G-valued Weil-Deligne representation. Okay, so the theorem we'll talk about today, which is our work in progress with Kisin, is the following. So we're going to assume L is not equal to P, and P is bigger than 2. Okay, and so I should say I think maybe these two assumptions based on current technology may not be too serious, and we have some hopes to get rid of them, but for now I'll keep this in the statement of the theorem. And I'll assume that A has semi-stable reduction at V, then we prove that these G-valued Weil-Deligne representations are defined over Q. So explicitly, so let me write down explicitly what this means. It means if we apply any theta, theta is going to be an automorphism of the complex numbers. This Weil-Deligne representation. This is conjugate in G to rho LB LBQG. Be true for all theta in the automorphism group. Let's get the Q. So it's defined over Q, and somehow, more importantly, they're independent of L. Okay, so this means for different primes L, these Weil-Deligne representations, G-value Weil-Deligne representations are conjugate in the smaller group G. Okay, for all L, not equal to L prime. Okay, so let me make a couple of quick remarks about the result. So remarks. So this a special case of this theorem is when this abelian variety has good reduction. So this good reduction case was actually proved in a previous work together with Kisin from a couple of years ago. Okay, and just like the classical case, the statement in this good reduction case becomes a little bit more explicit. So in this case, the G-valued Weil-Deligne representations are all unramified. So this means that the Weil-Deligne representation is essentially determined by the quantity class of Frobenius. So in fact, what we proved in this good reduction case, that there exists some Q-rational quantity class in G called gamma, such that this gamma is equal to the quantity class of ℓ-adic Frobenius for all L. For all L, again, L not equal to P. Okay, so in this good reduction case, we proved this by kind of reinterpreting the problem in terms of Shimura varieties. That was a question.
Yes, could see what you were controlling time so much. So kind of making time larger than the difference in stable reduction.
Yeah, you can. So I mean, you do realize semi-stable reduction are like a finite extension. Yeah. So you. Yes.
I think that we have didn't know you could achieve this line that you supposed. I mean, that's a deep line of the deep kind. And I mean, it's not really constructive stuff.
Okay, yeah, that's a good question. Yeah, yeah, I don't really know about that, but yeah. Okay, thanks. Yep.
If you state the theorem makes sense, I guess if the factorization of rho L through G is small. It's not just that it's the factorization.
Yes, exactly. Right, exactly. And this canonical factorization follows from the Betty et al. Comparison isomorphism. Yeah, thanks. All right. Thanks. Any other questions? All right. Okay, so this good reduction case we proved by kind of reinterpreting the problem in terms of Shimura varieties. So I know Mark gave a talk here in Bonn a few years ago about this. So I'm not going to say too much about the good reduction case. And so today I'm going to focus on how to prove this reduction. Sorry, this theorem in places of bad reduction. Okay, and another remark is, okay, there's also some work towards this conjecture by Newt. So he proves some weaker version of this conjecture A, where this this notion of conjugacy is replaced by some weaker notion. And maybe later on, I'll say a little bit about the relationship between our work and his work. Okay, so that was kind of the statement of the main theorem. So now I'm going to move on to discuss the proof. Yep.
When you say conjugate in G, does this mean conjugate by G2 or G2?
Oh, no, yes. These are all defined over C, so they're conjugate by some element of C. But this defined over Q just means that kind of the G conjugacy class is defined over Q.
But what does it mean to build a G?
Okay, G of C. Yeah.
So you mean the co-reduction phase when the representation is just given by an element of QL, you can only prove that given L they're like stably conjugate to something over Q.
Yes.
So in this case, you can't quite. So do you know that this gamma is literally QL conjugate to the protein ones?
No.
Almost.
Okay, almost, yeah.
Okay.
You might have to exclude a
You can choose, I think you can choose.
exclude a
The,
prime.
the question is if you can choose gamma, have that property for all L.
Okay.
So there's definitely an argument that shows true for, I think, all but one L.
Yeah, but actually, if the group is not quasi-split, you might not even get an element in of G in G of Q. So it's just a Q rational conjugacy class. But if the group is quasi-split, right, you can maybe ask this question, and the answer then is almost. You can just, exclude one place. All right. Okay, so let me move on to discuss the proof of this result. So I want to first give a fake proof of the result. Okay, so this fake proof, well, it doesn't work, but it's very instructive because it's essentially the proof that you want to make, but you're not quite able to. And the actual proof is going to essentially follow by adapting our setting to a situation where this fake proof does actually apply. Okay. So the fake proof is based on the following proposition. So first, the first observation is that this semi-stable reduction assumption implies that this Weil-Deligne representation, this p-value Weil-Deligne representation, is unipotently ramified. Okay, so unipotently ramified, mind you, just means that rho prime, this Weil representation part, is unramified. Okay, and for unipotently ramified Weil-Deligne representations, we have the following group theoretic proposition, which actually holds kind of more generally. That if G is some reductive group, is some reductive group over the complex numbers, and let's say you have ρ1 and ρ2 are G-valued Weil-Deligne representations, which are unipotently ramified, and Frobenius semi-simple, then the property that these representations are conjugate in G is actually equivalent to saying that they're going to be conjugate under all representations. Okay, so ρ1 congruent to ρ2 in G is equivalent to saying that I composed with ρ1 is conjugate in GLN with I composed with ρ2, and this is for all representations from the group into GLN. Essentially saying you can detect conjugacy if you can under all representations. Okay, so this proposition is completely group theoretic, but it's a little bit subtle. So in fact, if you try to prove this, I mean, this statement kind of makes sense for more general Weil-Deligne representations. So if you kind of try to prove this more generally, maybe without this unipotently ramified assumption, this you actually fail because it's not true in that case. So there are actually explicit examples of Weil representations which are not unramified, into some reductive group, which are conjugate under all representations, but they're actually not conjugate in the group G. Okay, so this proposition is a little bit subtle and really uses this unipotently ramified assumption, semi-stable assumption. Okay, so this is maybe one of the few places where the semi-stable assumption is actually used. Okay, but nevertheless, in the semi-stable case, this is okay. All right. So given this proposition, we can give the kind of proof of the theorem, proof in quotation marks. Okay, so let me just say for this main theorem, the kind of the more serious part is to prove the L independence. So once you have L independence, you can argue via some kind of Chebytarov density argument that these representations are actually all defined over Q. So really the main thing is to prove the L independence. And so let me explain how we can do this using this proposition. So we want to prove for L and L prime that these two different Weil-Deligne representations are conjugate in G. And this proposition tells us it suffices to check this under all representations. Okay, so let's just take any representation, I from G into GLN. Then we consider the GLN value Galois representations, I composed with rel G, and I composed with rel prime of G. Okay. So one thing we know about these representations is that they're actually compatible at unramified places. So this follows from the theorem in the place of at the places of good reduction. So our previous work implies that these representations, well, prime of G, are compatible at unramified places. And so what we want to do is compare the Weil-Deligne representations at a general place. And the idea to do this is to use the global Langlands correspondence to construct some auxiliary representation, which actually allows us to kind of compare these two. So we assume we know everything, everything we want about global Langlands for GLN. Then this should imply the existence of a representation RL prime. So this is going to be a representation from gamma E into GLN of GL prime bar, which is strongly compatible, with I composed with rho L G. Okay, so let me explain what I mean by this. So if we assume everything we want about global Langlands for GLN, then associated to this Galois representation should be some automorphic form for GLN. But then we can also kind of go back in the other direction. So associated to this automorphic form is some kind of compatible system of Galois representations. Compatible system of Galois representations running over all plans of the number field over which this automorphic form is defined. Okay, then if you even assume kind of local global compatibility of this correspondence, this tells you that this system is in fact strongly compatible, right? Okay, so this is actually what gives you this RL prime. So we're really assuming everything we want about Langlands for GLN, and it's really not hard to see this is where the proof it goes wrong. Okay, okay, but if we kind of assume for the moment that we can produce this strongly compatible system, let's explain how to finish off the proof. So the idea is now this RL prime is some representation into Q bar prime. So essentially, it's valued in the kind of same vector space as the representation I composed with rel prime of G. Okay, so that means you can kind of directly compare them using the Chebataro density theorem and Brouwer-Nesbit theorems. Okay, so we know that RL prime and I composed with rel prime of G are compatible at unramified places. So then applying Chebataro density and the Brouwer-Nesbit theorem tells us that I composed with rel prime of G and RL prime have isomorphic semi-simplifications. But it's known that this representation here is in fact semi-simple, and you can always take R prime to be semi-simple. So they're in fact conjugate in GLN. Okay, and so this just means the corresponding Weil-Deligne representation will also be conjugate. So I composed with rel prime of G, the Weil-Deligne representation conjugate GLN to the Weil-Deligne representation at this place V for RL prime. But by construction, this RL prime is strongly compatible with I composed with rel G, and so we also have the compatibility in GLN for the Weil-Deligne representation, or I composed with rel BWDG. Okay, and since this is true since I was an arbitrary representation, this proposition now implies that the original Weil-Deligne representations are conjugate in G. Okay, so that's the argument. And to kind of summarize, what we did was kind of use the global Langlands correspondence to show that under all representations of G, these Weil-Deligne representations are conjugate. But I should note here that there is a particular representation for which this kind of compatibility is already known, and that is this canonical Hodge embedding corresponding to the action of the Mumford-Tate group on the Betti cohomology. And so, in fact, what Newt does in his work is kind of extract as much as he can out of this particular representation, this particular Hodge embedding towards conjecture A. But somehow this extra argument using Langlands allows you to access kind of all the representations, and that you really need to get the full result. Okay, but of course, this argument, doesn't work. So the problem is that the problem is just on the existence of this kind of RL prime, this strongly compatible representation. Okay. However, this is not known for number fields, but there is a setting in which existence of strongly compatible systems are known, and that is in the function field case. So existence of RL prime, although it's not known for number fields, it is known for function field. We know function fields. So this is work of Laurent Lefort, the Langlands correspondence for GLN. Okay, and so the idea of the actual proof is then to construct some kind of function field avatar of our system of G-valued Galois representations. So in this case, this kind of avatar is going to be a system of G local systems on some smooth curve whose monodromy at a point on the boundary of this curve will realize the Weil-Deligne representation we're actually interested in. Okay. So there's a little bit of subtlety towards this because if you want to talk about the monodromy of some local system on a smooth curve in a function field, this gives you a Weil-Deligne representation for some equal characteristic local field, whereas we're interested in Weil-Deligne representations for mixed characteristic local fields. But again, using this kind of semi-stable assumption, you can actually kind of directly compare these two objects. And this is very plain to see if we consider the moduli stack of unipotently ramified Weil-Deligne representations. Okay, so now if I take F to be some local field, non-Archimedean local field with residue field FQ, then I can consider moduli stack of unipotently ramified Weil-Deligne representations for F. Okay, and in fact, in this talk, I and we'll only need to consider its complex points, which I'll describe as follows. Okay, so I'll define the set phi fg will be the complex points of this moduli stack. So it's going to correspond to sub-elements S and N, where S is a semi-simple element of G of C, and N is some element of the Lie algebra satisfying the usual compatibility condition for Weil-Deligne representation. So we require the adjoint action of S on N gives us Q times N. Okay, and we're going to quotient this out by GC conjugacy. Okay, and this you can kind of think of as the set of G isomorphism classes of Weil-Deligne representations. This is just because for G conjugacy classes of unipotently ramified Frobenius semi-simple Weil-Deligne representation. This is just because in the unipotently ramified case, this Weil representation is really just determined by a single semi-simple element, so where the Frobenius is sent to. So that's where this S comes from. And what you notice about this is that the set really only depends on Q, right? The size of the residue field, and not really on this local field F. So I can replace this F, in fact, by a Q. And so this actually allows us to kind of compare unipotently ramified Weil-Deligne representations for different local fields as long as they have the same residue field. Oh, it's a bit high. Okay, so based on this last observation, I'm going to make the following definition. So this definition is essentially going to be a kind of function field avatar of our G local systems. Okay, so define a realization of rho LG to be a triple is a triple x little x and LL for L not equal to P. Okay, so where this x in this triple is going to be some smooth curve. Over the residue field at B. This point x is going to be a point on the boundary of this curve. Okay, so it's going to be a point on delta x, which is just x bar. So x bar is some compactification minus x, and this is going to be some KED point. And LL, L not equal to P, is going to be a system of G compatible GQL local systems on X. Okay, so here G compatible means, okay, so you have these GQL local systems. So that means at each point on this curve, you can consider the Frobenius acting on the stalk of this local system. And this gives you some conjugacy class inside the group G. And the G compatible just means that these conjugacy classes means these conjugacy classes are independent of L. Okay, so it's kind of the analog of our results for abelian varieties at places of good reduction. So this is what this G compatible means on X. So these LLs are some kind of G compatible G local system on X, such that Okay, the monodromy at the point X on the boundary, which is just a Weil-Deligne representation, is unipermanently ramified. And most importantly, it's going to realize the Weil-Deligne representation that we're actually interested in. Okay, so this Weil-Deligne representation, so that corresponding to the monodromy at the boundary, is going to be equal to this rho LV WDG that we're interested in, and we can compare both of these as elements of the set phi AB G. Okay, just because these two different kinds of local fields have the same residue characteristic. Okay, so our second main theorem is just that there exists a realization. And the point of this is that theorem 2 now implies the main theorem, which I should have labeled theorem 1. Okay, so think that is theorem 1. Okay, so theorem 2 implies theorem 1, because now we can just, the fake proof actually works. You can just apply the fake proof to prove L independence of this monodromy at the boundary, and this you can prove using the argument I already gave. But now the global Langlands for GLN is known due to work of before. Okay. So that's the kind of the idea. So in the last I guess 15 minutes, I'll maybe say a few words about how we actually construct this realization. Are there any questions? Oh yeah, so I think essentially once you have Deligne's theorem, you can kind of forget about like Mumford-Tate groups and Hodge cycles. Once you have Deligne's theorem, you can just rephrase everything in terms of G local systems. That's kind of an important point. Yeah. Any other questions?
So I mean, you need some version of local global compatibility.
Yes.
In this balanced stuff.
Yes.
So, but for this group, we probably only need it for almost all places. Is it important to know it for all places? Probably just because it just need that.
You mean you need it to apply to the point on the boundary that you're interested in.
Sure.
Yes. But I think it's no for all points. Yeah. Yeah, it is. Okay. So let me explain now how to construct the realization. So eventually the way we're going to construct it is to actually realize this Weil-Deligne representation as the monodromy of some smooth curve on the special fiber of some integral model for a Shimura variety at a point on its toroidal compactification. Okay, but to kind of justify this, I need to introduce some other objects. Okay, so let's kind of focus. Firstly, let's focus on this kind of last condition in the definition of a realization. So that this kind of G local system actually realizes the Weil-Deligne representation we're interested in. So let's think about how we can kind of arrange this first of all. And the way we're going to do that is by considering some kind of two-dimensional schemes of the following kind. Okay, so we're going to consider this punctured affine line over the ring of integers OEV. So this scheme is equipped with two specializations. First, it has a specialization in equal characteristic. So it maps to this Laurent power series right, over KV, and it also maps to EV, okay, the completion of E of V. And this map is given by sending U to a uniformizer pi. On the right, you send U to just U. Okay. And the observation about these kind of schemes, okay, which is it's been known for a long time, is that these specializations induce isomorphisms of tame fundamental groups between this kind of mixed characteristic point and this equal characteristic point. So you have an isomorphism in tame fundamental group, the EV. Okay, so I'm using notation a little bit. I should really write spec of EV here, right? And Z bar is just some a geometric point. So this is in fact isomorphic, just the whole fundamental group of this scheme in the middle. Have another geometric point. And this is isomorphic. Now the tame fundamental group of this field in equal characteristic. Okay, and what this observation tells us is that, so this kind of isomorphism between tame fundamental groups tells us is, in fact, if you have a kind of a local system on this larger scheme, then if you take the kind of the monodromy in these two directions, they actually coincide. Okay, so if you have some LL, a GQL local system on the scheme in the middle. So let me call this spec of this, spec of this is Y. And let me call this point Y2 and Y1. So if you have some local system on Y, which is, let's say, unipotently ramified along these two directions, then we actually get an isomorphism between the associated, the Weil-Deligne representations along these two directions. Again, we're comparing them in phi G. Okay. So what this tells us is that, okay, if we want to construct a realization, one way to kind of at least ensure this last property is satisfied is to kind of show your local system or your Galois representation extends to some local system on some nice two-dimensional scheme. Okay, and you don't actually have to work with these particular schemes. This same kind of argument works to compare these Weil-Deligne representations. If you just take some some residually trivial étale cover of like the closed point in the affine line and then remove some divisor like this. Okay, so you work with some kind of more general schemes. Okay. Okay, so the problem then comes down to kind of extending the system of representation to some local system. And the way we do this is well, we're going to use a Shimura variety. So associated to our Mumford-Tate group and the Hodge structure on the Betti cohomology is a homomorphism from this Deligne torus into homomorphism for this Deligne torus, GR. Okay, so this, if you look at this conjugacy class, this gives rise to a Shimura datum. Okay, and so we can associate to this a Shimura variety, we'll call K, and this is defined over a number field called the residue field, which will always be contained inside our number field E. So we can just kind of base change to our field E that we're working over. This is Shimura variety. And I'll also let script SK denote an integral model for this Shimura variety. Okay, so I won't say too much about the precise assumptions on on the Schmorr variety, but just for the experts in the audience, I'll say that this integral model is essentially these Kisin-Pappas models, where the group at P is quasi-split, and we take very special level structure. Okay, so the Schmorr variety.
Yep. And the level group at P just needs to be chosen so that it contains the image of.
Yes, exactly.
So how do you guarantee that for all the different L's you can find that?
For all the different.
So what's the refinement on the level?
Like for different L's, it's a compact open at like a different place.
Sorry, so for this V, you need to choose a certain V.
Yeah, but the compact open, like for like L, right? The compact open is at the place L. See, right?
But this integral model is yeah, so this V is a place over P.
Yes.
And so what's the requirement of the level at P?
It's very special. Oh, you're asking what? Yeah. So okay, I should explain. Like, yeah. Sorry. Yes. So at P, you need to make an argument, and so you actually showed that. So I should say that this integral model is not actually for the one for the group G. It's actually some larger V restriction corresponds to this larger V restriction. So we showed that like there exists some kind of like the larger totally real field and the very special parahoric for this group, which contains the image. But that's some kind of technical thing which I didn't want to get into. Okay. The image of the Galois representation of P. Okay. All right. Okay, so the important thing about these Schmorr varieties, firstly, on the generic fiber, you can kind of think of them as some kind of moduli space of abelian varieties whose Mumford-Tate groups are contained in the group G. So in particular, our abelian variety A is going to correspond to some point on the Schmorr variety. That's the first point. The second point is that these Schmorr varieties, by their construction, are already equipped with some local system. Okay, so on this integral model, in fact, you have these GQL local systems as L runs over primes not equal to P. GQL local system on this integral model. And what we actually prove in our previous work, which is kind of the Schmorr variety analog of our result at places of good reduction, is that this GQL local system on the special fiber is actually G compatible. Okay. Prove that if you restrict this local system with this Schmorr variety base change to the special fiber, this is G compatible. Okay. So you have this local system, and in fact, these G-value representations coming from the abelian variety just correspond to pulling back this G local system on the Schmorr variety. Okay, and so if you want to kind of extend this local system to some local system on some larger two-dimensional scheme, this just corresponds to proving some kind of geometric property about these integral models. You want to show essentially this point corresponding to the abelian variety will extend to some point, some larger like point value in this two-dimensional scheme on this integral model. Okay, so the point is A corresponds, abelian variety A will correspond to some point XA on our Schmorr variety, which extends to a point which I'll also denote by XA. Okay. This extends to some OEV valued point. But now this point kind of degenerates to the boundary of the Shimura value. So this script SK sigma here is some toroidal compactification. So this sigma here is some kind of combinatorial data. You need to choose to define this compactification. And so the proposition, main geometric proposition we prove, is that there exists some residually trivial étale neighborhood of this closed point in the special fiber. The origin in the special fiber of this affine line over the ring of integers. So u equals pi equals 0. And some point x tilde of this toroidal compactification valued in x tilde. So some kind of point of this toroidal compactification valued in this kind of two-dimensional scheme, such that the following two properties are satisfied. So we acquired that under the specialization u equals pi, okay, we recover the point XA. Okay, so this u equals pi, well, strictly speaking, it's a point on this scheme, but it kind of lists uniquely to this residually trivial étale neighborhood, just because they have isomorphic Henselizations. Okay, okay, so we require that x tilde, if you restrict to this point, extends, so it extends XA, and we require that if you look at this special fiber of x tilde, this actually intersects the interior of the Shimura variety. Okay, and the way we prove this is to use the kind of the local description of the boundary strata in these toroidal compactifications given in this paper of Matafusi-Pera, where this toroidal compactification is actually constructed. Okay, then using this proposition, we can just construct a realization by kind of pulling back the local system to this special fiber. Okay, so if we take this LLG and restrict the x tilde tensor KEV. So now x tilde tensor KEV, this is going to be some smooth curve over the residue field.
X tilde is your neighborhood. Okay.
Oh, sorry, yeah, étale neighborhood x tilde x. Yep. Yep, thanks. So there exists some residually trivial entanglement. Huh? This is big x tilde. Little x tilde is the point. Yep. So big x tilde is the two-dimensional scheme, and x tilde is the point value in this. Okay, so if you just restrict this local system to the special fiber of this étale neighborhood, this is now a smooth curve over the residue field, and this will give you a realization. Okay, so if we look at the properties we require in a realization, we require that this local system on the smooth curve is G compatible, and this just follows from this. This just follows from this theorem we proved here about the compatibility of these local systems on the Shimura variety. And the last point is that we want this local system to realize the monodromy that we're actually interested in. And this just follows from this kind of observation here, and the fact that this monodromy arises from some local system on like these nice two-dimensional schemes. Okay, and so this constructs a realization. Now, like this whole argument that I gave using global lines can now work, and that you can use to prove the theorem. Okay, so thanks for listening.